This video will clearly explain the Qiskit circuit model, which is essential for quantum computing. Qiskit uses the quantum circuit class, which is the central object for creating circuits. It combines quantum and classical registers, gate operations, and measurements. The design is hardware-aware, modular, and compatible with both simulators and real quantum devices. Core imports include quantum circuit, AER for simulators, and the execute or transpile functions. Circuit creation involves defining the number of qubits and classical bits. Conceptually, time flows from left to right, qubits are horizontal lines, and gates are applied sequentially. The quantum register stores qubits and holds quantum states like superposition and entanglement. The classical register stores measurement outcomes and is used only after measurement. A key rule is that classical bits cannot control quantum gates. Measurement converts the quantum state into a classical bit, collapsing the superposition. The syntax measures qubits into classical bits. Measurements should generally be placed at the end to avoid destroying quantum information early. Qiskit offers tools for circuit visualization, including text-based diagrams, Matplotlib circuit drawers, and LaTeX-style professional diagrams. Visualization is crucial for debugging, explaining algorithms, teaching, and presentations. This scene provides an example of a Bell state circuit. This scene shows an example of a Bell state circuit. Transpilation converts a high-level circuit into a hardware-specific gate set, optimizing depth and gate count. This is important because real devices have limited connectivity, and transpilation helps reduce noise and errors. Real quantum hardware faces issues like decoherence, gate errors, and readout errors. Circuit design implications include preferring shallow circuits, fewer 2-qubit gates, and using error mitigation techniques. Best practices in circuit design include minimizing circuit depth, reducing CNOT usage, avoiding unnecessary measurements, and reusing qubits. Always test on simulators before moving to real hardware. Quantum circuits are used in various applications, including quantum algorithms like Grover's and Shor's, quantum machine learning, quantum chemistry simulations, cryptography, and optimization.